Hello, my name is Berend Smit, and we are now at the last part of our advanced molecular dynamics videos. Um, what we have seen in the previous lecture is a very formal way of writing the equations of motions in case we need an extended Lagrangian. And that is actually the idea of a Nose thermostat, is that we extend the normal Lagrangian with an additional variable in such a way that we generate the canonical ensemble. And that sounds abstract, and it is actually very abstract. It's nothing more but a mathematical trick, but it works, and it's quite interesting. And you'll see why we need the Hamiltonian and the Lagrangian formalism. And so let's see how it works. So what Nose proposed is if we simulate a system with this Lagrangian, we simulate the canonical ensemble. So what you can see here, it almost looks like the normal Lagrangian. So what was the Lagrangian? From the field, it's the kinetic energy minus the potential energy. And if you have the Lagrangian, you can write your equations of motion using the well-known, what we derived in our previous video, recipe. But the important thing is of the Lagrangian the Lagrangian is that you can write any equations of motion for any types of variables, and because this is this idea of the minimum path, that is the action becomes minimum. So what Nose actually did, he said, okay, let's extend our Lagrangian, and here we extend it with a variable s. So we now have a Lagrangian that depends on the velocities. So here the positions are important, and then it's r dot, this is the velocities. And we have now extended our Lagrangian with a new variable s, and the conjugate momentum here is this s dot. And what we can now do is we can now write the equations of motion. But what we also can do is we can write down the Hamiltonian, and from the Hamiltonian we can actually do statistical thermodynamics. So that's why we needed that previous the classical mechanics formulation of the Lagrangian. And what Nose proposed is if you simulate this Hamiltonian, and if we look at it in a special way, we simulate the canonical ensemble. So let's see how that works. So here, basically what you see here by analogy, so here we have the mass of our of the particles, and here this is the mass that is associated with s. So this is this variable q. It's a typical inertia with which the variable s varies. So we look at that here, and this vector g will become clear later on. So it's an extended system, n particles plus the variable s. So that's why we call this an extended system. So in order to derive the equations of motion, we need to define our conjugate momenta, our conjugate variables. So this is the conjugate momenta as given to particle I, which is then m s squared r dot sub I. And the conjugate momenta now for the variable s, which is the Hamiltonian, the derivative with s dot, and it's q times s dot. And it's very much like in momentum equation where q is the effective mass. So we also now can write the Hamiltonian. The Hamiltonian, that is in order to do statistical thermodynamics, we should have something that doesn't depend on r dot and s dot. No, it needs to depend on ps, on the momenta. So in order to get the Hamiltonian, we do this Lagrangian transformation where we multiply the variable where we want to get rid of, the r dot, with the value we want to have, the momentum, the conjugate momentum for particle I, and we do that for all particles, and we do the same for the conjugate momenta of S, which we would like to have, and we would like to get rid of the S dot in order to get the Hamiltonian, because then it depends on the position and the momenta, and we can do statistical mechanics. And that's important because we need to prove that we can actually simulate the canonical ensemble. So this is the way, the recipe of how we got the Hamiltonian from the Lagrangian. Okay, so this is our Nose Hamiltonian that gives us the same dynamics as the Lagrangian. So now, can we now prove that this thing is giving us the canonical ensemble? Okay. So we are almost there. Let's now introduce P prime, which is the momentum prime, which is P over S. And then this term gets a little bit easier. So we now have in P prime, this is the normal Hamiltonian, which is the sum of the kinetic energy, P prime, and the potential energy with this additional term. Okay, so the conventional Hamiltonian. So we now have a Hamiltonian, so we can do statistical thermodynamics. So we can look at the partition function of this particular system and also see what we sample. Okay, so if we solve Newton's equation of motion, we sample the NVE ensemble. So for an ordinary simulation, what would that be in terms of the partition function? So this factor is making it indistinguishable. We integrate over all possible momenta, all possible positions, but what we need to make sure in a microcanonical ensemble, that every configuration is equally likely, so has a factor 1, as long as it has the right energy. And in order to ensure it has the right energy, this E, we need to multiply this integral with this delta function. And this delta function ensures that only those configurations for which the Hamiltonian, which depends on the momenta and the position, equals E, survives. So this is selecting from all possible configurations, only those configurations that have this constant energy and the constant energy E. They have this energy E of the microcanonical ensemble. So if we would interested be in a different energy, we would select different positions and momenta combinations. Okay, and it's of course the same with the Hamiltonian for the Nose Hamiltonian, only this term is somewhat longer. We now have the S terms as well. So for Nose dynamics, the same thing. We now, since it's extended, we also have to integrate over all possible momenta associated with S, the conjugate momenta PS, and all the values of S. And of course, this is the trick that Nose is that Nose was using, because then the idea is that if we do this integration, the part that is left over is then in the canonical ensemble. But in order to show that, we need to manipulate this delta function. So if we substitute the Nose-Hoover, you basically get this expression, where we have switched the notation from P to P prime, so we get this S to the power 3n here. Okay, and then in these terms, in these variables, we have the normal Hamiltonian, so we need to get rid of those terms. Okay, so for that, we basically need to use some formulas, some equations that are associated with delta functions. So what do we have here? We integrate over the variable S. We have the derivative of a function the derivative S delta HS, and that is equal to this one. You can basically put that one here, and you see that is equal. And that is equal to the zeros of these functions. So where this, and this is just an inequality for delta functions. So if you have the derivative of a function s and the delta function s, so this holds. So basically, the delta function of hs is the zeros of the delta function of divided by the derivative of s. These things are typical properties of delta functions, and you can sort of see that it makes sense here. And but for the moment, we just assume that this equation is correct. So for our case, we see here, we have a few of those terms where we would like to see the derivative. And what is then very important is to look at this logarithm. So h prime, if we take the derivative here, h prime is, because of the logarithms, is 1 over s, because the other terms do not depend on s. So the solution of this one, the zeros of hs, so when is this term 0? It's basically given by this equation then. You can easily verify if this is hs, the 0 term, the solution where this is 0, you can just substitute that, and you see then by definition this is 0. Okay, so we have this Hamiltonian, we have here this delta function. So if we then take these results from the derivative here, and we have this factor here, we basically can substitute this expression. So we basically transform this into the 0, the zeros of this function. So if we do this integration, we basically only left with this term. So if we now carry out the integration, we see that we have this thing here. And if we take things out and select g equal to 3n plus 1, so we can carry out this integration. We can carry out this integration. It's giving a constant we left with here. And you see, if we take g equals down, we get a Hamiltonian that surprisingly looks similar to the canonical ensemble. Since the constant plays no role in thermodynamics, so that's more or less showing that with this Hamiltonian we can simulate the canonical ensemble. So this is then the Hamiltonian, and the conjugate variables are this, and here we now get the equations of motion simply by the formula we have derived in the previous section. So what is the idea? So what we do is basically here we simulate a system with an extended variable s and ps. And if you look at the math, it's a little bit complicated, but the idea is actually relatively simple. The idea is, in these extended variables, we simulate at a constant Hamiltonian. So this Hamiltonian is constant. But that constant is basically chosen such because of this functionality, that if it's constant, and with this particular form of P and S, if we just focus on this part and this part, it is actually occurring in a probability that is exponential minus beta the energy. That is exactly corresponding to the canonical ensemble. So what you basically do is you extend your Hamiltonian or your Lagrangian, so you add those two variables, and you do it in such a way by choosing this functional form, and that has to do with this mathematical trick of the delta functions. The remainder is almost by magic sampling exactly the canonical ensemble. And that is a marvelous trick, because that is a way, by extended ensembles, you can simulate the canonical ensemble, and you're not dependent anymore on this collision. So if you look at it, what is this? If we look at the P prime there, it's basically a slight rescaling of all the coordinates, of all the momenta, all at the same time. So that is what you do in in a Nosy-Hoover simulation. So instead of giving one particle a random kick, this collision with the Anderson demon, we scale all the particles a little bit all at the same time. You have to be careful. It's still not realistic dynamics, but it's a much milder form of perturbation, and as a result you can expect that it has less effects or less dramatic effects on the dynamical properties, and normally they're actually quite small. And here you have the equations of motion of the S variables, and this is something, if you then apply the Strotter expansion for with these kind of things, you can immediately derive the equations of motion. So we see that irrespective of the mass associated with the S variable, we do simulate this Maxwell-Boltzmann distribution, and here you do see an effect of the mass. So here I did a simulation at the temperature T is 1, and then at this time step I switched that, I set the target temperature to 1.5. And then you see if the mass is relatively small, you get these large overshoot and the system responds very quickly. And here, if the mass is very high, you get a much more moderated response. But in the end, you see the fluctuations are the same. The end results does not depend. As you see here, this is a measure of these fluctuations. It doesn't depend. So here we now have the diffusion coefficient, and you can see it really doesn't depend on the value of Q. So it may actually be quite reliable. But again, if you absolutely want to be sure, you're much better doing a simulation. Here you stop and you do an NVE simulation, because that is certainly the correct dynamics.